Okay, hi there, Dr. Matthew J. Trom here again. This is now the second follow-up lecture just to cover the slides that I didn't get to talk about in my course introduction earlier today. So I just want to talk a little bit about my course goals. And here they are. And if you read them, they probably don't seem particularly academic. So let me give you kind of a little explanation and maybe a little bit of background to explain why these four things are my goals for EML 4501 for MEC 2. So the first one is to teach you to embrace and solve open-ended engineering problems. And, that sort of seems like, really obvious, but you'd be surprised because all of you for the past 15, 16, 17 years have basically been taught to solve problems in sort of a closed form, convergent type way, right? Where we basically tell you, some underlying theory, some equations that you can apply. We give you a word problem, and there should be one really clear, easy, obvious way to take the information given in the word problem, plug it into the model that we've already taught you, and you crank through some arithmetic, and poof, out comes an answer. And then you flip to the back of the book, and voila, the answer that you calculated is the one that's in the back of the book. You got the problem right, good for you, and you get to move on to the next problem. Design does not work that way, and problem solving in design is not linear. It is divergent instead of convergent, and it is really going to challenge those of you who kind of embrace this idea of closed form solution type problem solving, which most of you do because you've been taught to do it that way for years and years and years. And so this becomes very challenging for me as an instructor. I end up almost every semester getting in some pretty heated battles, some pretty heated arguments with students about the way that we do problem solving in design. And it's particularly hard for the high performing students that have been super successful solving problems in this linear fashion for 15 years to get to where you are now in your fourth and final year of college. So the reason that we teach you guys to embrace and solve open-ended problems is not only is that the way that it's done in design, but that's what happens when you get out into the real world, right? You're never just given a word problem that fits into a nice box of fluids or mechanics and materials or dynamics, and you could just apply the theory from one class to solve the problem and it's done, right? Everything in the real world is interdisciplinary. There's multiple ways to solve problems. There's also different answers, right? And some answers might be better than others, but they're all potential answers. And so we need to get you thinking this way so that you can be successful when you transition out into the real world. And the reason that this is so important to me, here comes another war story, is that when I took design at UC Irvine 20 some odd years ago, I was not a convergent, open-ended thinker. I was very, very sorry, I was not a divergent, open-ended thinker. I was very convergent and very linear in the way that I saw problems because I was essentially trained as a scientist, right? Okay, I got an engineering degree, but engineers are basically, scientists that know how to do design in some cases. And so I was in the design class, and the problem that we had to solve was to take a square piece of ice from an ice cube tray and try to stick it into the mouth of like a water bottle, right? So like one of those Aquafina water bottles, half-liter water bottles. And the solution that my team and I came up with was what we called the Appliance, and it literally looked like this when we built it. So this is a commercial product that's made by GE, but our product was essentially this. And so what we did was we actually took the square or the cube pieces of ice from the ice cube tray and we dumped them into a reservoir. We then melted them down into liquid water, and then we recast them, refroze them into a cylindrical form factor so that the cylinders could be dropped into the water bottles without any problems. And we were so proud of ourselves. This was awesome, right? We brought this thing to class. It was all automated. It had all these lights and buttons and things. We had to plug it in because it took so much power to do this. because we were melting water and refreezing water. We actually built a refrigerator into the thing, a freezer into the thing, so that it could do the ice freezing. I mean, this thing was awesome, right? It was like literally a tabletop kitchen top appliance that, had we done like one more design iteration, it would have literally been this thing that General Electric sells today for $600, and this was 20 some odd years ago. So we bring this thing into class, we present it to the teacher, we're so super proud of ourselves. This is obviously the best possible design for putting square or cubes of ice, basically a square peg in a round hole, right? These cubes of ice into the cylindrical top of a half-liter water bottle. And then guess what happened? The group that came after us, right? And I should mention that my group was like all of the best students in the class, right? So all the super high performing, magna cum laude, summa cum laude, top performing students. The group that came after us were basically the screw ups, right? The guys who never came to class, who didn't know how to, add numbers, who were just not good students. But so one of them sort of stumbles in and pulls out of his backpack a water bottle like this. Another one pulls, the ice cube tray out of the freezer that we had in the laboratory to generate the ice cubes, takes a couple of ice cubes out of the ice cube tray, shoves them into this bladder, this water bottle, and then the third guy on this team pulls a hammer out of his backpack, boom, smashes the ice cubes up in this water bottle, and then they open up the bladder and they dump the crushed ice into the half-liter water bottle, and that was their design solution, right? They basically spent all of 15 minutes trying to figure out how to do that, and in the end, their design was the one that was selected by the instructor as the best design to solve that particular set of customer needs, right? Putting a square cube of ice into the circular mouth of a half-liter water bottle. And I never forgot that. That to me was sort of the moment where I became a design engineer, because I realized that, as awesome and cool and wonderful as this solution was, it truly was not the best solution, right? We took a huge amount of energy, a huge amount of cost, a huge amount of time to develop this thing, and really the right solution was just to smash up a bunch of ice cubes so that they fit through the mouth of that bottle. So anyway, that's a little bit of a war story, but I did want to share that with you because, like you, I used to be very linear and very convergent in my thinking, and it actually took this real world experience in my own undergraduate design class to realize that this was better than that. Even though this looks awesome and this looks kind of dumb, it turns out that this is a better solution, at least for that particular problem. So just wanted to share that story with you guys. Okay. So the second course goal is to really prepare you for professional practice and or for graduate school. So again, this ties back into the first one in that if we are having you start to think divergently, that's much more in the way that a design engineer in practice actually thinks. If you happen to be going into grad school, you're going to be solving open-ended research problems, right? You have to solve problems in order to get a master's degree and a PhD that have never been solved before. That's the definition of an advanced degree. And so you will have to think in an open-ended and divergent way in order to be successful, either if you go into practice, professional practice, or into grad school. And so we want you to be prepared for that, and we want to give you kind of a crucible of that experience where you have real deadlines, a real external customer, you're feeling, real-time constraints, you're having to manage your time, schedule time, work in groups with other people to come up with a real design that you could present to a customer and present to a panel of practicing engineers, go through design reviews so that you have experience doing that. And all of these experiences that you're going to partake of in 4501 are all meant to prepare you for what happens in the real world, either in professional practice or when you're on your way to grad school. So that's my second goal, is to get you guys ready. And that, of course, leads into the third goal, which is to make you more attractive to employers by producing work products that you can showcase both to potential employers, and if you happen to be going the route of graduate school, to graduate programs that you might be applying for. Now, I've already told you that you guys are the best of the best. You are elite because you are University of Florida students, and you're fourth year students, so you've gone through the entire process to get where you are now. And so you are already incredibly attractive to employers. And what we are going to pile on top of that already sort of attractive feature that you guys bring to the table is a series of work products from the class that you'll be able to share with potential employers to show them how amazing you guys are and the high quality and high caliber of work that you can do. So by the time this is over, you guys will have posters that you will present at research symposia. You will have written reports that describe your design process. You'll have a final kind of product presentation, a slide presentation that we're going to record and post up so that you can share that with potential employers. And so by the time you're done with this class, you're actually going to have a portfolio of work products that you'll be able to take with you after the class is over and share those things with potential employers just to let them know how much experience you have doing product development, product design, and how well prepared you are for engineering practice or for graduate school for that matter, right? Because you have to do a lot of the same stuff in grad school that you do in practice, especially presenting your work and generating new ideas and new concepts. And so then the final thing, which seems very, very weird, is to equip you with what I call war stories for interviews. And this really is anecdotal. So, engineers are people who do things. We build things, we create things that never existed before. And that's what really differentiates us from scientists who sort of have this theoretical understanding and knowledge of the world, right? The difference between engineers and scientists is that we are actually the doers that take the knowledge and put it into practice for the benefit of humanity and for civilization. And so in order to prove to potential employers that you are an engineer, it is very important to have a series of kind of war stories about things that you've done. So I could tell you, and I won't, but I could tell you stories about the time that I accidentally made it snow in my laboratory because I opened a dewar in the wrong way and sprayed liquid nitrogen all over the place. I could tell you the story about the time that I turned the basement laboratory at one of the universities that I used to work at into an ice skating rink by accident. There's all kinds of these stories that happen when you gain the experience of actually doing something. And engineers like to hear those stories because they validate and they confirm that you guys have that hands-on experience that we engineers as doers value. And so in this class, you are sure to develop a number of kind of interesting, funny war stories. And even though it seems like a weird thing to why would I tell a war story in an interview? I kid you not, every single time, I've been teaching capstone design for more than 10 years now. And every single time I send my students out, to job interviews, they always come back and they always say, I spent a good chunk of my time talking about capstone design and talking about that time that I, did this thing wrong and learned from my mistake and improved, and the next time it actually worked, right? And the employers actually wanted to hear that and know about that and know about my capstone project. A lot of employers will just straight up ask you, what was your capstone project? And so it's really good and really important to have those war stories in place, those stories of, things that you learned, things that you did, real world experiences to share when those questions come up for your job interviews. So really important in my mind to equip you with those war stories so that you guys, again, are more attractive to potential employers because you have that real world experience. So those are my course goals. Now, of course, one of those goals is to prepare you for professional practice. And professional practice, at least for an undergraduate engineering degree program, is defined by ABET Outcomes. So ABET used to be the accrediting body for engineering and technology. Now it's just ABET. The acronym doesn't mean anything anymore. But ABET has 7 learning outcomes that it actually measures on a regular basis. So an ABET auditor will come to campus and make sure that we are hitting these 7 learning outcomes in all of our ABET accredited undergraduate engineering programs. And the ones that are the most strongly tied with Mech 2 with this class are the first five. So to solve complex engineering problems using science and math, to apply engineering design to meet specified customer needs within realistic constraints, to communicate effectively within a range with a range of audiences, to recognize professional responsibilities of engineers and make informed judgments, and to function effectively in a team. So those are the top five. And then of course we do the other two, right? We have you develop and conduct experiments, analyze, interpret data and draw conclusions, and of course acquire and apply new knowledge. But it's really those first five that the department assigns to EML 4501 that we as the instructors, or I as the instructor, am responsible for assessing. And so you guys will see these again, right? These five actually will come up in a lot of the assessments that you guys do throughout the semester. And so, just be aware, again, there is a method to my madness, right? So just be aware that I am looking at how well you are doing these things, evaluating you, assessing you, so that you are very well prepared for professional practice and the department's ABET accreditation, which is critical, to make sure that you can sit for things like the EIT exam, the PE exam, get a professional license if you want one, work on federal government contracts and so forth. That all of those things are in place, so your degree continues to have value. The other thing that I want to do to prepare you for professional practice is to get you up into the high levels of Bloom's taxonomy. So Bloom's taxonomy is a very kind of venerable, well used kind of learning strategy or learning tool, learning paradigm that basically looks like a pyramid, right? And as you move up the pyramid of Bloom's taxonomy, you are doing more and more and more cognitively complex tasks. So at the bottom of the pyramid are things like remember, understand, and apply, right? Where you're recalling facts, or you're explaining concepts, or you're using, information in a new situation. So we give you some sort of, theoretical background, and we ask you to solve a new problem with the theory that we already told you. And it's probably no surprise that those three bottom levels of Bloom's taxonomy is basically where you have been for most of your engineering education, right? We've asked you to memorize a bunch of stuff, we've asked you to understand concepts, and we've asked you to apply theory to solve problems in the back of the book. In EML 4501, right, again, if I go all the way back here to teaching you to embrace and solve open-ended engineering problems, we are pushing you to the top three tiers of Bloom's taxonomy, which are to analyze, evaluate, and create. And so it's those three top tier skills in Bloom's taxonomy that you really need to be successful in professional practice. And so analyzing, that is drawing connections among ideas. So this is the idea of interdisciplinarity, right? So this class has prerequisites, fluids, dynamics, Mech 1, and DML. And you guys are going to be mixing and matching concepts from all those different classes, bringing them together, synergizing them together, pulling in concepts from other classes that aren't even prerequisites for this class, and using all of that stuff to analyze something new that has never been created before, which is this major project for the customer that we'll be doing in the context of the class. We're going to ask you to evaluate, right? So you're going to look at a bunch of different possible solutions to design problems, and you're going to justify why you picked a particular solution against a backdrop of all the other possible solutions that you could have picked. And then ultimately we're going to ask you to create, right? You guys are going to produce a completely new product from a set of customer needs that has never existed before, that is not commercially available for a customer that really needs it, right? So this whole semester, we're going to push you up to the top three tiers of Bloom's taxonomy. And again, for a lot of you, this is going to be uncomfortable, right? Because this is not the way that you guys have been taught to do engineering up until now, but it is absolutely critical to get you guys transition from being students to being practicing engineers, that you guys learn to think and operate on those top three tiers of Bloom's taxonomy. So So that's the method to my madness. Okay, so that's what I wanted to talk about with respect to my course goals. I'm going to make some follow-up lecture videos describing how to use the Canvas site, and then ultimately I'm going to review the syllabus, course schedule, and share with you some of the class expectations. But I've talked for 20 minutes, and so this is probably a good time to stop this particular video. Thank you guys for your time, for paying attention, and look forward to seeing you in the next one. Okay, bye. Thanks.